All right, so for the first part of the lecture today, we're going to just review a little bit about Laplace transforms and why we need to use them for our process control class. So again, you won't likely use a Laplace transform in your job ever. Some people do if you do, if you work in, the mathematical side of it, but they're really useful for us here. And primarily the important thing for you to think about, for this class particularly is these are just going to be used as a tool to solve differential equations. So it's a method for us to solve differential equations. Ultimately, what we want to do is express outputs in terms of inputs. And by using the Laplace transform, we can do this in an algebraic way. Last time in chapter 3, we worked on developing dynamic models. And these dynamic models are equations that relate a output variable to input variables or other variables within the process. So I'm going to kind of go through a couple of things fairly quickly. So I'll start by showing this is the definition of what the Laplace operator is. So the Laplace transform operator means this. So if we apply the Laplace operator, or you could say take the Laplace transform of a function of t, so our function of t. As an example, we could say f of t. So the function of t could be something like dy dt. This could be a function of t. A function of t could be just y of t. A function of t could be t squared, etc. So to apply the Laplace operator, we're going to take the integral of the function that we have, that we're taking the operator of, integral from 0 to infinity, of the exponent raised to the negative st dt. And what this is going to do is this is going to convert from the function of time to the function in what's called the Laplace domain, right? So this is going to be the function in the Laplace domain. Function in time to function in the Laplace domain. And we'll see what that is. So we could do an example. So if we wanted to say, for example, let's take, we have f of t equals just t, right? In other words, the way that you could think about this, because a lot of times we're used to talking about things in terms of x and y. If you have something that's called, y of x equals x, right? This is essentially the same thing that we're doing there. So we're taking the f, which is a function of t, as it relates to t. So we know this right here, y equals x, is just a linear relationship. So this right here would just be a linear relationship. We can make this x squared, and then we have the exponential, etc. Okay? So in order to take the Laplace of this function, we would just go integral 0 to infinity of t times e to the negative st dt. All right. That's where we are. How do we take this integral? Someone chime in and help me out.
Integration by parts.
Yeah, so we would have to do integration by parts on here. And so we would have to, looking at the function, looking at this, we would have to look at, this is one term and this is another term. When we do integration by parts, we have, and again, I'm just going to write up here. So integral of u dv equals uv minus integral of v du. And then this right here is evaluated over the limits of the integration, and this integral would be done over the limits of the integration. Okay, so in this term, we would do integration by parts. And then this would give us something like, when we end up solving we take the derivative, or we take the integral of this, it would give us something like 1 over s squared. I think this is correct. I might have to pause for, I don't want to spend time to actually go through and do this, but yeah, so this is correct. In order to do these Laplace transforms, I put some links on Canvas that bring you to some, again, if you go to YouTube and look at how to apply the Laplace operator to any function, they'll go through and they'll do that for you. For this class, we're not gonna, so I think that you should be able to do this for a couple of different functions. And so the functions that I think you should be able to do this for, so I made a list there. So maybe something like a times t, b times t squared. Also, it is useful to be able to do it for an exponential of a of t or sine of a of t. So these are the general forms, and I'm not gonna, I'll tell you, I'm not gonna ask you to do any of these on a test or anything in terms of, you know, as an engineer or as a person who's taken process controls that involves Laplace transforms, at least being familiar with how to take the Laplace transforms of these. I think that's something that you can do. So look over, maybe just take a minute and look at those videos. This one right here is maybe most useful. This one right here would be good. And if you can do those two, you can pretty much get all of them. Okay. The good news, okay, in this class, again, we're not going to spend a lot of time applying Laplace operators. And the reason for that is because these Laplace operators have already been done on the common functions or the functions that we'll need. So if you noticed previously, we had an equation that looked like this, like tau times dy dt plus y equals k, I'm just going to call it this, k times u. And in this case right here, y is a function. So y is our output function and u is our input function. This right here is a first order differential equation. The reason why we use, if we take the Laplace operator on a first order differential equation, we convert it from an ordinary differential equation into an algebraic equation. If we have a system of equations that are written as algebraic equations, they're much easier to solve than a system of equations that are differential equations. Okay, so the general method that we're going to use is we derived our process models. We did that in chapter 3. Okay, so now in order to be able to come up with transfer functions or to solve the process models, our process is going to go as follows. We're going to apply the transform to each equation. We're going to solve to get the algebraic form of y of s, and then we're going to take the inverse Laplace to get back to y of t. Okay, so to solve a differential equation, we use the Laplace to convert this to an algebraic form. We solve the algebraic form in terms of y of s, and then we convert back to get to y of t. And we'll show an example here. Right, so this is shown here, maybe graphically. So in this case right here, we start from our differential equation. We apply the Laplace. So in this case, we're applying the Laplace operator of this whole equation. And because it's linear, we just apply the Laplace operator of each term. This first term right here is the Laplace of dy dt. And the second term right here is the Laplace of f of t. Okay, but this is written in a very general form. We don't have this right here. I'll show some examples in just a second. Once we have it in this form, once we apply the Laplace operator, then we rearrange everything to solve for ys. Right? So we just rearrange the equation and solve for the function y in the s domain. And y in the s domain is going to equal just a bunch of stuff that have s's in it, but you can't have y over here. Our y is on the one side. Right? So that's just like rearranging an equation to solve for a specific variable. And then once we go here, we take the inverse Laplace of here. I didn't show you how to do the inverse Laplace. What we're going to do in this class is when we do this part right here, number 1 and part number 2, all of these are going to be done using Laplace tables. Okay, so we're going to use a table that's already solved the Laplace transform for us. To do this part up here, we just do some algebra. So we're going to have to do a little bit of algebra to rearrange things. Okay, so part one and part two, we're going to take the Laplace transform by using a table. And so this table in the textbook, and I also put this table on Canvas, is about all you need to know to apply the Laplace transform. I'm going to just point out a couple of things on here. If I were going to, okay, so if you're not with me, this is a good time to maybe pay attention. So I would modify my table that looks like this. This first term right here, I'm going to cross off this ramp input, or I might just cross this whole thing off. And I'm probably just gonna, I would rewrite this as A times T. Okay, for this term up here, just to be consistent, I'm gonna just call this term A. So if I take the Laplace of A, the Laplace of A, and A is just a constant, equals A over S. Okay, if I take the Laplace of A times T, okay, in this case, A is a constant, so A is going to come out of the operator, so this would be like A times Laplace of T. Laplace of T is just 1 over S squared, so this whole thing equals A over S squared. So what this table shows is in some cases there's a constant that's outside, right? Like here's there's a constant outside. Here's there's not a constant on the outside. If I put a constant on the outside right here, like if this said take the Laplace of A times T squared, right? It would just be A times 2 over S cubed. Scrolling, I guess we kind of moving down on here again a little bit, you can see that in this case there's a constant out front, but that's related to the constant on the inside. Again, you might have to apply some constants. This right here has a constant on the outside. So my point here is you can put a constant in or out, but this shows the general form of taking the Laplace operator. So when we take the Laplace, we go in this direction. Now if we want to take the inverse Laplace, so the Laplace goes in this direction, the inverse Laplace goes in this direction. So when we have equations, like we will derive our process models, rearrange them, get them into the form that we want to. In general, the tricky part is not going in this direction, because we just have to look at what is our term over here, and we just apply what it is. The tricky part can be going in the inverse direction, so taking the inverse Laplace. The way we take the inverse Laplace is we have to take what our function is, and we have to rearrange it so that it looks like something in the table. And when we rearrange it, for example, to make it look like something in the table, then we can go back in this direction. Okay, so that's going to be where we do the majority of work. Let me point out a couple of other things. I showed you on the previous slide the Laplace of the derivative, so df, the Laplace of the derivative of a function equals this right here. S times f of s, so this is just the function in the Laplace domain, minus f0, and this right here is the initial condition. And it's the initial condition in the time domain. We're going to do, one of the things that we're going to do for our transfer functions is we're going to set the initial condition, or we're going to set everything relative to the initial condition and work in what's called deviation variables such that the initial condition is 0. And I'll show you what that means as we go forward. Okay, a couple other things. So here, if we want to look at, here's the Laplace of sine. It would look like this. Again, I think this would be something that maybe watch the video to see how that works. Okay, so in general, our Laplace transforms for this class, it's going to just be a tool, and the tool that we use is going to be this table. But you should still understand a little bit about what the Laplace operator means. Here's another slide. This just kind of has a couple other things about, or another way of representing the same things on the previous slide. Okay, so one of the things that we can do to check to see if we took the Laplace transform correctly is what's called the final value theorem. And I think there's a homework problem that asks you to do this. But again, this is more of a check than anything else, just to verify that our work is correct. So this says is that the limit as t goes to infinity of f of t equals the limit as s goes to 0 of s times f of s. Okay, so we can use this to check to see if we apply the Laplace operator correctly. One of the things for the final value theorem to be correct is it has to be bound. So if f of t goes to infinity, this isn't necessarily going to work. Okay, so the initial condition, initial value theorem, it's also a good consistency check. What that says is the limit as the function goes to 0 should equal the limit as s times the function in the Laplace domain goes to infinity. Again, you can do those for either one. Okay. The next part, the remaining couple slides that we're going to look at, these slides, they're not necessarily related to doing the Laplace, but there's something that we need to do in order to be able to go and use the Laplace transform to solve for something. So an example, and I have this worked out on here, so I can just talk through it instead of writing through it. So an example might be, right, let's say for example, we applied the Laplace transform and we ended up with a function that's y in the s domain equals this right here. When we apply once we apply the Laplace operator, solve for y of s, the next step is to do the inverse Laplace. And so what we have to do is we have to make it look like something that looks in this table. So the things that show up in these table, right, we can kind of see we have these terms that look like this. There's various other terms. The purpose, once we get here, is that now what we have to do is we have to make this look like values that look from the table. And one of the ways that we can do that is called partial fraction expansion. So what that means is a lot of times if we have these products or roots in the denominator, we want to break those apart to make them look like this, because terms that look like this show up in the Laplace table. Okay, so partial fraction expansions, what that means is that this fraction right here can be expressed in this way, right? So it can be expressed as something over s plus 2 plus something over s plus 3. And then again, the way that we figure out what these terms are in the numerators of each side, right? So if I multiply this side right here by s plus 3 over s plus 3, and I multiply this side by s plus 2 over s plus 2, now you can see here that everything over here is under the same denominator. Okay, so again, we go through and do that, and then what we see is that s plus 1 equals these terms up here. Then we rearrange and solve, so we know that the terms multiplied by s have to equal 1. So a times s plus b times s equals s. So we have that equation. And then we know that this term 1 has to equal, so the constants have to be equal. So 3 times a plus 2 times b equals 1. And so we know this is true. And then we can solve these two equations and then get this. Okay, so once we now get this equation that looks as shown here, we can pick these things out of the table right here. So if I can now, right, this is now our y of s. So y of s equals this function, which equals this. So I'm going to ignore this right now because I can't do the inverse Laplace of this one, but I can do the inverse Laplace of these two individually. Right, so the inverse Laplace, now I'll just write it right here. So inverse Laplace of -1 over s plus 2. I'm making a mental note of that. I'm going to go back and look at my table. So this term right here, I had -1 is my constant, s plus 2. So the inverse Laplace of s plus 2 would be e to the -2t. So over here, I get -1 times e to the -2t. Okay, then the inverse Laplace of this one is going to be the same. So the inverse Laplace of 2 over s plus 3 is going to be 2 times exponent of -3t. And then again, inverse Laplace, I didn't write this one, the inverse Laplace of y of s equals y of t. So here now we can see that now y of t is going to equal negative exponent to the -2t plus 2 times exponent -3t. So we have now solved our differential, or we solved our differential equation for y of t by using the Laplace. And we used partial fractions expansion in order to do that. Okay, so let's kind of go through, here's an example shown right here. So here's a second order differential equation shown here. The initial condition is given. This one, it sets it up pretty easy that the, since it's a second order, we need two initial conditions. So we have the value of the function at 0 equals the first derivative at 0 equals 0. So the initial conditions are 0. And that's helpful because, again, if we take the Laplace of this term, go back to the table, Laplace of the second order is s squared times fs, and then it's going to be minus s times the initial condition, and this term was 0, and then it's going to be minus the derivative evaluated at t equals 0, which is also 0, so that's just going to give us s squared times fs, which is this first term. So this term right here now, the derivative of this is going to be, or the Laplace of the derivative is going to be s. So we have 6 times s times ys. The Laplace of y is just going to be y. And then the Laplace of a constant is 2 over s. Okay, so what we did here is we took the Laplace of each term. Now what we have to do is rearrange and solve for this term right here. And you can see that we solve for this term by just factoring out s squared plus 6s plus 8. And then we ended up dividing it through to the other side. So we solve for y of s. And so the s squared plus 6s plus 8 is just this right here, but this was also factored. Okay, but we can't go to the table and we can't take the inverse Laplace of this whole function because it's not in the table. So what we need to do is we need to break this apart into the individual terms. And when we apply the partial fraction expansion, and again, I'm not going to go through the details right here, but again, it applies similar to what we did on the previous slide. We end up getting the term ys as still as a function of s, but now we can take the Laplace of all of these individual terms. And then by taking the Laplace of all of the individual terms, we end up solving. So here we take the Laplace of the individual terms and we solve for y of t, which is the solution to this initial differential equation. So again, Laplace is used to solve for differential equations. In addition to just being able to apply the Laplace operator and the inverse Laplace operator, we have to go through a little bit of a mess of algebra in order to get things to look like they look in the table so that we can use the Laplace as the tool. Here you can look, we can apply the initial and the final volume theorem to check the work here. I'll let you look over this one later. It's just plugging some numbers in and checking. And so that's all for the, let's see. All right, so now for the second part of the lecture today, I'm going to introduce transfer functions. And this is from chapter 5 of the textbook. And a transfer function is essentially, it's a Laplace domain model that shows the influence of one process variable, the input, on the output. So a transfer function is going to be, it's a function in the Laplace domain that relates an input to an output. And the general form of a transfer function is shown here. So we typically use g as a term to represent transfer function. We typically use y to represent the output function, and we typically use u to represent the input function. Okay, so again, this is convenient because if we can represent the output function y as an algebraic form, and we can represent the input function u as an algebraic form, we can simply just take the ratio of the two. So again, this will give us an algebraic form that relates the input to the output. It doesn't have any derivative or differential terms in here at all. So we can use, so g of s can represent any individual process. So the g of s can represent the chemical process. In that case, we might call it gp of s. It can represent an actuator, where we would call the actuator GA in the Laplace domain. Again, the sensor would be GS, the controller would be GC, or we could have a combination. So we might call this G overall equals such and such. So the Laplace transfer function relates any output to any input. Okay, but this is typically going to be single output, single input. Now, one of the benefits to here, like we showed previously, if we have an actuator, a process, and a sensor, we showed that the output of the actuator is the input to the process. The output of the process is the input to the sensor. So we can use we can use these transfer functions to combine all of these individual processes together to come up with one overall transfer function. And again, we can use that for open loop processes, and we can do that for closed loop processes as well. Again, so the transfer function, one of the important things to note is the transfer function it's what's called a normalized model. So the transfer function tells you how the output changes with respect to the input, but the input can be any function at all. So the input function doesn't matter with respect to the transfer function. The transfer function can be the same, but your input can be anything that you want. And by knowing what your input is, then you can end up solving for your output. Okay, so what I mean is that if we know G of S equals Y of S over U of S, and if we have a function or we have a model for this term right here, if we know what U of S is, so for example, if U of S is a ramp or a step input or a sinusoidal input, we can solve Y of S equals G of S times U of S. We can do this for any input. So once we know the transfer function, we can solve for our control variable or output function relative to any single input that comes into the process, right? Obviously, if the input varies, the output's going to vary, but the transfer function is not dependent upon what the input function is. Okay, in order to do this, we're gonna learn a couple things. So for the derivation today, again, this is not a derivation that you're going to have to be able to do over and over, but the importance of the derivation that we do, it helps us explain or understand specifically what a transfer function actually is. And so when we do a transfer function, we work in terms of deviation variables. So deviation variable means variation from steady state. Okay, so we're going to write our models, we're going to convert them into the deviation variables. And so essentially what the transfer function tells us is that if the input changes by a certain amount, the output changes by a certain amount. It doesn't tell us the absolute value of the output relative to the absolute value of the input. It's essentially, it's a change in output relative to a change in an input. So that's the important thing, is it's going to be deviation variables relative to the steady state values or the initial condition or whatever the initial value of the function was. These are all going to be linear models. So everything in here in a transfer function, everything must either be S or a constant. And then finally, the thing that's extremely important, and again, if we don't necessarily apply the transfer function to solve for how the output variable changes, so we might not necessarily do that. One of the things that's extremely important about a transfer function, and we'll talk about this next time, is the transfer function indicates the dynamic behavior of the control variable. So if we know what the transfer function is, we can tell whether or not the process will have oscillations, whether or not the process will be stable, or other interesting characteristics that might be exhibited by the process, right? And this is really what's most useful to understand how the process can change. And you can tell this just based on the form of the transfer function. That's something that we'll look at next time. Okay, for our example that we go through today, we are going to do, we're going to derive a transfer function for a mixing tank example. But again, we can do this for any chemical process. Okay, so the mixing tank example that we're going to do, let's see, so we have F1, we have two streams, F1 and T1. It looks like this right here is our control valve. So our manipulated variable is going to be F1. So this is what we change. We can see that we care about the temperature of the stream coming out. because we're measuring it. So this is going to be our control variable. And then we have some other stream that shows up in here. Other things, so the other things that we can note, we're going to assume that in this case right here, we're going to keep the volume constant. So if this were a real process, we might have a level controller that varied the outlet flow such that we kept the total flow rate coming out is equal to F1 plus F2. Okay, so we're gonna treat that as a constant. Okay, so the first thing that we need to do to derive our transfer function, and so we're gonna come up with a transfer function for this process, is we have to derive the transfer function, or we have to derive the process model. So step one in our transfer function derivation is going to be the process model. And this is something that we did last time. So the process model, so we derived the dynamic model, and just maybe to go back here, we started from the general form of the energy balance, which is dmu dt equals the sum of the energy coming in is F1 H1 plus F2 times H2 minus the sum of the energy coming out, which is F times H. But remember that F right here equals F1 plus H1, or F1 plus F2. We could do the same thing. If this had a heater on here, for example, if there was a Q, we would put a Q on here. If there was a steam jacket, electric, we would do that accordingly. But for now, so we started from, this is our general form of the energy balance. Actually, I should put hats on here because these are specific energy, specific enthalpy. M is the mass of inside the tank because the accumulation term is what's inside the system, and our system is the contents of the tank. Okay, so what we did last time is we rearranged this in terms of measurables, and we came up with a process model. So our process model for this case was M times d temperature dt equals F1 T1 plus F2 T2 minus F1 plus F2 times T. So one assumption that we made here is that the heat capacity, the constant volume heat capacity and the constant pressure heat capacity are equal because it's a liquid. And so in all of these terms, we would have factored that out, and then we rearranged some things to get it into this form. This looks remarkably similar to this, but that's only because we don't have any extra terms. If we had a heater on here, the heater would be divided by at least the heat capacity term. Do we want to put Q on here or just leave it as is? I'm going to put Q on here. So I'm going to say our process right here also has a heat transfer rate. And I'm just going to say, I'm going to call Q. And this is going to be, we're going to say a constant rate of heat addition to this process. So we have, this could be like an electric heater, for example, that adds heat at a constant rate. If that's the case, then over here, I would have a term that has Q over Cp. And the reason why I'm doing this is because this is a constant. Okay, so step one is process model. That's what we did from chapter 3. Step 2 is now we're going to define in terms of deviation variables. Okay, I'll stick to my notes on here. So for this process right here, we have our output variable. We have to define T in terms of deviation variable. So what that means is my deviation variable, I'm going to call T hat equals T minus T bar. And so T bar is my steady state. So this is going to be the steady state condition, or the initial condition, the steady state. T hat is the deviation. This is our steady state. And this right here is just our variable temperature, right? So in other words, we can say that T equals T hat plus T bar, right? So we defined our variable in terms of deviation variable plus our steady state condition. Okay, so for this case, if we knew all of these terms could vary, we would have to write them for each term. But again, we're looking at like a single input, single output process. So we're going to assume that temperatures are constant. So we're not going to put those. No, I'm sorry. We're going to say that the flow rates are set to be constants, and maybe the temperatures of either one of these streams can change. So we're going to define deviation variable for each temperature. So T1 equals T1 minus T1 bar, and T2 hat equals T2 minus T2 bar. We can do, these variables right here aren't related. In most cases, when we derive a transfer function, we're just going to do a single input and a single output. Because the textbook does it this way, I'm keeping it in this form, and these variables aren't related, so it doesn't necessarily matter. You know, we could just treat T1 and call that fine. But we'll do it this way. So, okay, also now, so now T1, or let's see. Okay, so now we define everything in terms of deviation variable. So this is going to be T hat, T1 hat, plus T1 bar, and then T2 equals T2 hat plus T2 bar. All right, so now you can see that these variables right here, the next step that we're going to do is we're going to plug them into the equation. So this is going to go into here, and this is going to go into here. T1 is going to go into here. T2 is going to go into here. And then we can rewrite. We can continue here. So define the process variables and simplify. So now if we do this, we're going to end up with m times the derivative of t, which is t hat plus t bar dt, equals f1 times t1 bar, t1 hat plus t1 bar. That would be t1 plus f2 times, this is going to be t2 hat plus t2 bar minus f1 plus f2 times, this is going to be t, which is t hat plus t bar. And then we would have plus q over cp. Okay, so we just plugged in the deviation variables for each one. Okay, so the next thing, so we put it all together. The next thing that we want to do is, right, if I back up here, this right here, this equation that we wrote, this equation has to hold true at all conditions. So at the initial condition, this equation is satisfied, but this term right here would be 0 at steady state, right? As the temperature changes, this equation has to be satisfied. So we can write this equation at the steady state condition, and it has to be valid. So this is valid over all conditions, all temperatures. Okay, so at T0, we know that m times dt bar dt, right? At steady state, this term is actually, we know this is going to be equal to 0, equals f1 t1 bar plus f2 t2 bar plus f1 plus f2 times t bar plus q over cp. Okay, this is true at the steady state condition. If I go up here and I look at this equation right here, so what I want you to see is that up in this equation up here, if we take this term, I'm going to underline these terms, this term multiplied by the front, this term multiplied by f2, this term multiplied by f2, and then this term over here, the derivative of this would be equal to 0, but we have it over here. The sum of this term plus this term plus this term plus this term, which are all these terms right here, the sum of these terms equals 0. You're following me? So this term plus this term plus this term plus this term equals 0. the derivative of this term right here is 0. Therefore, I know that m times d dt bar dt, right? So this would be left over. So this term is not 0, but the derivative of a constant is 0, equals f1 times t1 bar plus f2 times this is t1 hat, t2 bar, or t2 hat, minus f1 plus f2 in parentheses times t hat. So this right here now gives me my equation, again, written in terms of deviation variables. It looks like what I did is I just canceled out these terms. I didn't cancel out these terms. What I did is I know that the summation of this term plus this term plus this term plus this term equals 0. So I could rearrange this and write this as this form. I could write it as all of these terms plus then all of those terms and just group all the other terms. So these terms we know are all equal 0. And this gives me my final equation written in deviation variable form. So one thing that I want to note is that when we do this process, when we convert to deviation variable and then we subtract out the initial condition, or we set the initial condition equal to 0 because it is 0, once we do that process, any constants that initially showed up in our model equation should go away because those constants are there at steady state. And because we're looking at deviation variables, just whatever the constants tell us about the relative magnitude of these different terms relative to each other at steady state. In terms of deviation variable, now this doesn't necessarily matter that much. Okay, so now we go ahead and we take the Laplace transform. Also, I want to note, because this is in terms of deviation variables, that means t at 0 equals 0, t1 of 0 equals 0, t2 of 0 equals 0. Because it's in deviation variable, all the initial conditions are 0. So we take the Laplace transform. Laplace transform of this term is going to be s times t of s. So we have s times m ts. And let's see. We would subtract this right here. We might need to, actually, so this is t, so we can we'll write this as t hat of s. Really what this is going to be is s times, let's see, the Laplace of this term right here is minus the initial condition, so it's minus t hat of 0. But again, we said this term is 0 because all the initial conditions are equal to 0. The Laplace of this term right here, it's just going to be the function equals f1 times t1 s. The Laplace of this term is also going to be the function plus f1 times t2 s, and then minus the Laplace of the last one, which is, it should be f2. f1 plus f2 times the Laplace of this function is just going to be the function itself. So the Laplace of t is just t of f. Okay, so here we have to do, which step? Now we rearrange the process and solve for the output variable. So at this point, we want to go ahead and solve for t of s, and that's our function. So again, I'll take this term right here, and I'll bring it over to the other side, or essentially like add it to both sides. So we'll have s times m times t of s plus f1 plus f2 times t hat of s equals f1 times t1s plus f2 times t2s. And then again, we can do a little bit of rearranging on here to solve for T of S. So essentially factor out these two terms, divide over through the other side. And so, I mean, we're factoring the TS out and we're left with the other term. So TS is going to equal, I'm going to split up these terms over here. And so now this is going to be F1 over M times S plus F1 plus F2 times T1S plus F2 times M times S plus F1 plus F2 times T hat 2 of S. So now here is my solution, or my representation of T in terms of the input variables. So this is my output right here. T is output. T1S, this could be one input. T2S, this could be another different input. Okay, so remember what we said is that a transfer function is the ratio of a single output to a single input. So if we look at what we have right here, this right here is now going to be our transfer function. Our transfer function related to temperature 1, and this right here is going to be the transfer function related to temperature 2, right? So what this means now is, I'm going to write this up here, that space. So G1 of S equals the output, which is T of S, over the input, which is T1S. Note, going forward, I'm not going to write the hats. Whenever we have a transfer function, the transfer function implies that it's in terms of deviation variables. So as we go forward, writing the T hats on here is a little bit redundant. It's going to be assumed that this transfer function is in terms of deviation variable, so we don't have to carry this through every time, right? So now this transfer function right here, this is flow 1 over the total mass of the system plus the combined flow rate. This right here tells us, it's going to tell us how the temperature changes with respect to changes in the input temperature T1. Notice that these two transfer functions are very similar to each other. And the reason why these two transfer functions are similar to each other is if we go back and we look at the process model, the two temperatures have the same effect on the process. They both affect the process the same way. And the relative effect is related to the relative ratio of the flow rates, F1 to F2. Okay, and so we can kind of see that here. So this one, if F2 is smaller, it's going to have a smaller effect. If F2 is bigger, it's going to have a larger effect on the temperature. All right, so that's, again, so maybe summarized a little bit right here, kind of groups it together. Here is the one transfer function, here is the other transfer function. And so overall, what this says is that TS is equal to G1S times the input function 1, T1, plus the second transfer function times the second input. And typically we just do this for a single input. This is a unique case. I mean, this was an easy case to do because we know if we're mixing two streams together of different temperatures, the temperatures of each stream are going to have the same effect on the process of the temperature. It's just a ratio of the flow rates. When you have variables like this that have effects on the process the same way, the transfer functions are essentially additive. Or so the processes themselves are additive. Okay, another way we can express that is shown here. Okay, so we said that the temperature of the process, the effect of the transfer function of the process is going to be additive to the transfer function of the one input times this transfer function plus the product of the second on it. So, this one right here is essentially like, TS relative to changes in temperature 1. So if temperature 2 stays constant, this is going to define how T changes. If temperature 1 stays constant and temperature 2 doesn't, this will be 0, and this is going to define how the temperature changes. But if they're both changes, they're both going to have an additive effect on the process. We can represent that through, this is right here, like we talked about last time. This is the logic flow diagram. That should look like diagram. Right, and so the way that we're expressing this is here is the one input times the transfer function. So this T1 multiplied by TS, this is going to give us I should give us, this is going to be TS, and I'll just call this maybe A. So it's the effect due to the first process. This one right here, we can just give this a term T sub B, because again, the total temperature of the process is going to be the combination of the effect of changing temperature 1 times its transfer function plus the effect of changing temperature 2 times its transfer function on the process. Okay, so these are two, this is the combination of two parameters affecting the same process. Therefore, they're additive. Okay, so what else? All right, so this is, I guess, kind of what we just previously said is that, you know, we can use if the stream 2 is held constant, then the temperature is only defined based on the changes of 1, and we can determine what that transfer function is there. If we want to go and use this further, if we want to actually end up solving for temperature as a change, so if we want to, now what we're doing here is we're going to make a change to this input, and we want to use the transfer function to solve for how the temperature is going to change as a function of time. In order to do this, what we have to do is first take our input function, and if we know we input function in the time domain, we have to convert our input function in the time domain to an input function in the Laplace domain. So again, like we said, we can have any function for this input, but what we're going to do for this example is we're going to do a step change in T1. So what a step change in T1 is that if we plot T1 as a function of T, right, at some condition, at some point, let's say T equals 0 right here, we're applying a step increase in temperature, right? And we're going to define the step increase as A. So what that would mean is that at some point we were at T1 0, and now we're at, our new condition is T1 0 plus A, right? But because we're in terms of deviation variable, it's going to be this change. If we want to write this as a function T1 of T, so the representation for T1 as a function of T is going to be T1 0 plus A, and this is going to be applied at T equals 0. So that's the definition of a ramp, or that's the definition of a step input change. So the step input change is just a function. If we want to now convert this in terms of deviation variable, T1 hat or T1 bar equals T, what do we say? T minus, or T1 minus T1 bar. Right, in this case right here, this T1 bar is the, actually T1 bar. So this, I'm going to delete this right here. Okay, this is our initial condition. So in this case right here, T1 bar equals this term T1 0. So therefore we have our deviation variable for T1 equal to just A. So if we want to express the input, the deviation variable of temperature 1, it's just going to be this change. It's just the change from the steady state condition. So that makes sense. Okay, now what we have to do, look at, is, right, this has to be in the Laplace domain. So if we take the Laplace of A, we go to the Laplace table, and the Laplace of a constant is just going to be A over S. So now up here, we would replace this with A over S, which is shown on this slide right here. So the temperature, so again, deviation form of the temperature equals the overall transfer function times the input. And we said that this right here is a step input, which has this function. And this right here is our transfer function. Okay, so then what we do now is we would have to, if we want to, again, solve this, we can rearrange this to make it look like something in the table, then take the inverse Laplace. And so let's, if you want to make a note of this quickly, and then go back to the table. I actually don't have the table. I'm going to bring up the table. I'll leave that there. And let's come back to find our Laplace table. Okay, let's see if we can find it in this table. I think that equation looks something like this right here. Okay, so maybe make a note of these. If we take the inverse Laplace of this term, it looks like this. It's going to give us a times 1 minus e to the negative t over tau. We just need to make sure our equation looks like this. So if we go back, and now we come back to our form that looks here. Okay, so this, we need to make it look like this. We need to make this look like a +1 term over here in the denominator. So we can do that. And this is going to look like a times f1 over, I'm dividing everything through by f1 plus f2 over, right? So I combine these terms. I'm dividing the top and the bottom by f1 plus f2. And then over here I have m over f1 plus f2 times s plus 1, all of this multiplied by s. Okay, so now what we can see here is if we go back and we look at the other relationship, this right here from the table is our tau. This right here is our a term. Okay, so now when we apply the inverse Laplace to this, going over here to the next slide, we're going to have t in deviation variable is going to be equal to that term a. So that's going to be a times f1 over f1 plus f2 times 1 minus exp of, this was like t over tau, or negative t over tau. So this is going to be negative f1 plus f2 over m times t, parentheses. Okay, so this is now, we solved for temperature in terms of, this is the temperature as a function of time. It's shown right here. But now remember, this is in terms of deviation variables. So if we want to solve for temperature as a function of time, it's going to be whatever t naught, the initial value of the temperature, plus this term right here, which I'm not going to write again. Or we can write this, we can call this one right here t of 0, or maybe we can just call this t naught. Okay, so now plotting, if we plot temperature as a function of time, it's going to look like this. This is essentially a first order exponential decay towards the new steady state value. So here's the old steady state value, here's the new steady state value. This type of dynamic behavior is described as exponential, and what it is initially the change is really fast, and then it has an exponential decay towards the new steady state value. Okay, so this is what the function would look like if we plotted it and solved it as a function of time. Again, and then if we look at the general form of this, it's a first order form of a, it's a solution of a first order differential equation. Okay, so let me see where we are. Okay, so let's, if you're with me for a second, we're going to do this example right here and then we'll stop for the day. So let's derive the transfer function for a process, for a level process, where here's the dynamic model that we've described previously. This could be something like, so this would be a process like, imagine we have a tank, right? If we have level in a tank where we're saying the change in the level is related to the flow in minus the flow out, but the flow out is a function of the level. So this would be like an example of a gravity drain tank. But we know that if it were a gravity drain tank, we would have level to the 1/2. We can't actually treat level to the 1/2 right now because we have to have linear models or linear equations, and L to the 1/2 is not a linear equation. So next time we'll talk about how we take nonlinear equations and we make them linear. This is something people don't really like to do either. Like Laplace, another bad word is Taylor series approximation. So next time we'll look at Taylor series approximation to linearize nonlinear terms. But for the sake of ease, let's just look at it right here. So we have our control variable L, we have our input function Fn. So we want to see how the level changes as F1 changes. So our transfer function is going to relate L over Fn. And again, these are going to be in terms of deviation variable, but because it's a transfer function, it's implied that it's deviation variable. Okay, so the process is we put them in deviation variable form. So we have F n, so F hat n equals Fn, or actually, I'll write it this way. Fn equals F hat n plus Fn. And then we also have L equals L hat plus L bar. Okay, we put these, let's see if I have, okay, I'm going to use the next slide. Okay, I'm going to put these in here into this equation. So we have A rho D, and this is going to be L, which is L bar, L hat plus L bar dt. Fn is going to be F hat n plus F bar n minus K times L minus K times L hat minus K times L bar. I just distributed this through. Okay, so this is our equation. This is in terms of deviation variables. Then we also know that at steady state, the level's not changing. So at the initial condition, the level's not changing. So we can write A times rho times dL dt equals 0 equals F in bar minus K L bar. All right, so therefore, this term equals this term minus this term, or this term minus this term equals 0. So I'm going to, if I group these two terms together, I know the sum or the difference is equal to 0. So finally now I have A rho dL hat dt equals Fn hat minus KL hat. So if I go back and look at this equation right here, all it does is it looks like I replaced my variables with hats. I mean, that's sort of true because there's no other constants that show up in here. A shortcut that people sometimes make is it's just going from the process equation to the deviation variable form is just delete the constants and replace the functions with hats. I mean, I think that works most of the time, but this is why, because going through this process here. Okay, so now we take the Laplace, and remember the initial condition of L equals 0. So this is going to be, again, now I'm taking the Laplace. So I'm going to have, again, A rho S times L in the Laplace domain. I'm dropping the hat because I know now in the Laplace domain it has to be deviation variable form, equals Laplace of this term is just going to be the function Fn in the Laplace domain minus K times L in the Laplace domain. I'm going to group the L terms over here together, bring all the L terms. So I have on this side, L in the Laplace domain is A rho S plus K. Brought that over to the other side, equals Fn in the Laplace domain. So now again, I want to solve for my overall transfer function, which is output, which is L over input, which is Fn. And again, so L over Fn is going to be 1 over A rho S plus K. So this right here is my transfer function, and I suppose I could write this G of S for the level and its effect of Fn to the process. Okay, so I'm going to, let's see. I'm going to stop there for today.